So we're here to present the life and death of kernel object abuse. I'm Salf. I'm a senior security software engineer at MSRC, and this is Ian.
Hi, my name's Ian. Hello. My name's Ian Kronquist.
Now, I'd like to begin with, when I'm facing any kind of problem, I like to look at the anatomy and try to dissect it into much smaller, much simpler problem. And we need to answer three specific questions. In my case, it's the why, the what, and the how. Starting with the why, I think there is definitely a method to madness. If we look at modern kernel exploit techniques, it usually starts with some sort of exploitable bug, like a use after free, out of bounds write, or an integer overflow. The next step is to try to gain a higher exploit primitive, and usually by abusing certain type of objects to ultimately gain arbitrary read and write to the kernel memory. And after you gain arbitrary read and write, it's the process so simple to leak the eProcess token and assign it to your current process or to any other instantiated process and gain higher privileges in the Linux kernel. Which moves us to the what. We're going to go through a simple intro into memory corruption bugs, several types of memory corruption bugs, and then explain in details what object abuse and how we can abuse these kind of memory corruption. Starting by a simple UEF. If you look on your left, I think, on my left, and this is just a simple pseudocode for a vulnerable function to use after free. It starts by allocating a new object to memory, and then during a certain condition, the object gets freed, but then the function operates on that object without further checking that the object was freed or not, which results in some memory corruption and operating on freed memory. Now, how would you usually exploit that? Is that just after the object has been freed, we try to allocate an object of the same size and allocate it to the same heap or memory location to replace the previous object. And then if we make the assumption that object C, the last object that was allocated, has member X, which has the value of 1, if we operate on the dangling pointer from object A, the first object that was freed, and we try to modify the value of its B member to 41, 41, 41, or any other value, when we try to print object C's .x member, it will be equal to the value that was modified by the other dangling pointer. Of course, this is a simple demonstration on what can actually happen. The results may vary depending on the object and what member of that object that you can overwrite, which we're going to present later after we go through the memory corruption bugs. The next type of bugs I want to talk about is x86 integer overflows. So if you look at this calculation, FF 80 plus 81 on 32-bit systems, the calculation will result in 1. Well, actually that's wrong. The real calculation result is 01000001. But since 32-bit registers are 4-byte wide, it cannot hold this value. And thus, the most significant byte gets truncated, and the result of the calculation is equal to 1. This is what we call integer wrapping or integer overflow. So the integer has lapped over the max int value and resulted in a much smaller value. And we will see in the next slides what this will have impact on functions and several scenarios. So the first impact can be through linear overflows. We have two scenarios in that case. The first one is that we allocate an object of a size that has been overflowed, meaning that there were some calculations prior to using that size argument on the size that was supplied by the user, resulting in an overflow just like we explained in the last slide. The second scenario is that the object is allocated using a fixed size. So after the object has been allocated to memory, the first scenario, if the memcopy function or any data copying loop was using the user supplied size, the original size, not the calculated size or the overflowed size, that means that we will actually overwrite adjacent memory, since it's trying to copy a large number or a large amount of data into a much smaller allocated memory location or region. In the second scenario, if the data copying loop or data copying function is using a user supplied size without checking that the user supplied size is larger than the fixed size of the object, then it will result in a linear overflow. And the reason for linear is because you overwrite adjacent parts of memory. The next issue that can happen is that if we start by allocating an object with an overflowed size, again, some calculation happened on the user provided size that resulted in a much smaller allocation than originally intended. And then somewhere during the function tries to write to a specific index. If that index is larger than the overflowed size, that will result in an out-of-bound write into an adjacent memory, and thus we can manipulate near or nearby objects members and pointers and everything in memory. Now, how would we exploit out of bounds and overflows? So first we need to get the kernel memory in deterministic state. This can be done using pool spraying, and it usually involves a series of allocations and deallocations in kernel memory. And then we create memory holes by freeing parts of these objects, and hopefully the vulnerable object will be allocated to in one of these memory holes just before a user-controlled object. And then when we get to the overflow or the out-of-bound write, we corrupt interesting members of the user-controlled objects. And that brings us to the last question of, is the how. So what constitutes an interesting object? What members do I need to override to gain a higher exploit primitive? We can start by an object that has a data size member. If you are able to corrupt the data size of an object, then if you can extend it, it means that when you read and write from it, you'll be able to read and write past its original allocated memory. Add pointer to data. This would allow arbitrary memory read and write. So a pointer to data, if you are able to override the pointer, it means when you operate on the object later on, you're operating on a user-controlled pointer in kernel memory. And hopefully that object will have certain interesting functions like get data and set data, which will allow read and write from the object's memory in the kernel. So going through the theory of how I would abuse objects for fun and profit, and how would you actually do that? If we consider that we have two allocated objects adjacent to each other in memory, each have 100 bytes of data, and then a certain exploit came and we corrupted the first object's data size member. This will actually allow us to extend the object size and allows for relative read and write. So in theory, we would be able to read past the object's data up to 4 gigs depending on the corrupted size. And then we can use the main object with the relative read and write to set the next object or the adjacent object data pointer to whatever pointer we need. In that case, we set it to 41, 41, 41, 41. And that means that when we try to read data from the second object, we will be actually working on a user-controlled object or a user-controlled pointer of 41, 41, 41. Of course, in real-world scenarios, this data pointer needs to be changed to something that would be interesting to us, like, as I mentioned, the E-process structure or something like that. So Win32k memory has several types of memory. First is the desktop heap, which contains anti-user, or it's dubbed anti-user. It contains window management-related objects. You all know window objects, menus, classes, and such. And objects are allocated and freed using RTL allocate heap and RTL free heap. The second memory type is the page session pool, which normally contains anti-GDI objects and some anti-user objects, but we'll focus on anti-GDI objects for this talk. So the GDI-related objects are like bitmaps, path, palettes, brushes, DCs. Many objects that get allocated are used by the GDI subsystem in Windows. Objects are usually allocated and freed using xallocate object with tag, xallocate pool with tag, and xfree pool with tag. Also, there is the run page session pool, which is not in scope for this presentation. Here we look at some statistics from the MSRC cases that we've seen so far that are related to those specific user or GDI objects being abused to gain a higher exploit primitives, as we explained. So we see the number one object is surface object, which is the bitmap. And the second one is the tag window object, which is a window object. So let's start by the second most famous one, because historically the tag window object was being used much more or older than bitmaps being used, so that's what I wanted to explain. This is how the tag window object, or it's a snipped code of how the tag window object actually looks like in memory. So you can see I've highlighted some interesting members. So you have the buffer and the CB window extra. So the buffer is a pointer to the window name, and the CB window extra is the number of bytes or extra bytes that this window have in memory. And the part highlighted in green is where this extra memory actually is. I think you can begin to see how this is going through. So if you're able to override the CB window extra or corrupt it in some way, you'll be able to read relative to the window object in memory into adjacent memory. If you're able to corrupt a buffer pointer, then you'll be able to read and write from anywhere in memory. Now, this was the case a long time ago, and this has been mitigated by Microsoft recently. There are many other ways that you can abuse the tag window object, but I just want to discuss the basics of how we can actually abuse it. So let's look at how we can create windows. It starts by I'm sure a lot of you know, like create window and create window X functions. This is normal. That's how you allocate a window in Windows. And you can free a window using destroy window function. Also, so how can we read and write? Or in that case, we can read data. We can use get window long or set get window long pointer and internal user get text. And what these do is that it will read a long at a specific index into the cbwind extra or extra bytes from the window. The second function, which is internal get window text, will read maximum length string or up to length string, which is less than maximum length string, from the buffer or the window name buffer that is pointed to by the window object. The next set of functions is how we would write data. And it's a set window long and set window long pointer. And then the second one is a system call called anti-user def set text. And it's used to set the window object's name. So the way we would exploit it is that set window long pointer will actually write a specific long at a specific index that is less than the cbwind extra structure. And the anti-user set def set text will write up to length of string that is less than maximum length string to a specific pointer that is pointed by the buffer. Now, moving on to exploiting this kind of technique, if we allocate two window objects adjacent to each other in memory, we could use a kernel bug to actually corrupt the cbwind extra of the first window object. And then this will allow us to gain relative read and write into the adjacent memory of the next window object, which means that the window A will be the manager object that we will use its relative and read and write capabilities to actually overwrite certain or interesting data members of the second window object, which will be the worker object. So window B will be the worker object. We will use the relative read and write to override the adjacent window's string name buffer or the buffer pointer to the string of the window name. And then we would use read and write functions that for the second window to actually read and write from an arbitrary location in kernel memory. The next technique I want to talk about is abusing bitmaps or surf object. And this has been heavily used in the past 2 to 3 years. It was initially disclosed by Keen team at, I think, CommSec West back in 2015, but it was heavily detailed and analyzed by Nico Konomo and Diego Juarez of, at the time, Core Labs. Now I think Nico is at Bluefrost, over the period of 2015 and 2016. So the bitmap object in kernel memory is actually dubbed surf object, and it has a pool tag, or in the object header is GH5 or GLA5, depending on which memory location it gets allocated to. For GLA, it's look-aside lists, and GH is the normal page session pool. And this is how the object looks like in kernel memory. You can see that I've highlighted a couple of interesting members. First is the sizzle bitmap, which is the size of the bitmap. It's the width and the height of the bitmap. And the next one is the pvscan0, which is a pointer to the bitmap data in memory. Now, a lot of you might think that bitmaps allocated from user mode is actually allocated in user mode memory. But because it's a GDI subsystem, it's actually getting allocated into the kernel itself. How we can allocate bitmaps is by using the create bitmap function. It's available for any C++ program. We can delete or free the object using delete object function. We can read data using get bitmap bits, which will read up to size of the bitmap from the address pointed to from pvscan0. And then we have set bitmaps bit, which writes up to size of bitmap data into the address pointed to by pvscan0. Again, going through the scenario, if you allocate two adjacent bitmaps in memory, you overwrite or you extend or corrupt one of the sizzle bitmap members, which is the width and height, meaning you extend the bitmap size in memory. You'll be able to read and write past the bitmap into adjacent memory location, which contains our second bitmap. And that means that the first bitmap will be the manager that will be used to set pointers to read and write from the second bitmap. Second bitmap will be the worker object. We will overwrite or use the relative read and write to override the pvscan0 member of it with any value that we need. And then when we use get bitmap bits or set bitmap bits on the second bitmap, we'll be able to read and write from arbitrary memory location. The next object I'm going to talk about, we haven't seen many cases about. I just want to talk about it because I found it. So it's palette objects or colored palettes in memory. This was disclosed by me at DEF CON last year. And that has interesting values because starting from RS3, bitmap technique was killed, as will be explained by Ian in the next part of the talk. So I was working on a specific exploit for a kernel elevation of privilege exploit during my previous employer before I got employed at Microsoft, and the bitmap technique got killed. I needed to find some way to actually abuse or gain higher memory primitive, and luckily enough, I found this palette object and was able to fully exploit the vulnerability. So the palette object has the object type palette and has the pool tag GH8 and GLA8. And this is how the palette object looks like in memory. You can see I've highlighted several interesting parts. The first interesting member is the C entries, which is the entry count of the color palettes for that specific palette that are located in that specific palette. The next entry is the P first color pointer, which actually points to the APAL colors array, or the palette entries in memory, which is allocated at the end of each palette object. We can allocate palettes using create palette, which takes a logical palette structure. This logical palette structures contain the palette entries and the palette entry array, which contains a list of palette entries. Now, what's interesting about that is that it allows you very granular and controlled allocations and deallocations or frees into the kernel memory, which can be used for kernel spraying and getting kernel memory in deterministic state really easily, or used to be, I hope. So this is how in code you can allocate a palette into kernel memory from user mode. You can also free palettes using delete object. You can read data from a palette using the get palette entries function, and that will read up to n entries starting from a specific index from the data that is pointed to by the address of P first color. And we can write data. There is actually two functions that can be used to write data to palettes. There is set palette entries and there is animate palette. And these function will actually write up to n entries from in a specific index into the data that is pointed to by the pointer of P first color. Now you can see how palettes can be very powerful, specifically that it allows you to write specific amount of data to a specific location that you can control, and we will see how we can abuse that in a minute. So we start by allocating two palettes adjacent to each other in memory, palette A and palette B. We use a kernel bug to corrupt the C entries member of palette A. That will give us relative memory read and write into palette B's memory, which is adjacent to palette A. And palette A will be the manager object that will be used to set or set the pointer that we will read and write from later on. Palette B will be the worker object. We will actually overwrite, you will use the relative read and write that gained in the previous step to override the P first color pointer of the second palette. And then we use palette B, set bitmaps, set palette entries, and get palette entries to actually read and write from an arbitrary location in memory. Now, there is a specific restrictions to that technique. If you look at these members in front of you, the HDC head, the P transform current, and the P trans old, if any of these members get clobbered, then it can result in a blue screen of death, or it can result in an error without reading or writing data. Several posts have been out there by BitShifter, a friend of mine, and I think Kozenek, detailing the restrictions and how they were able to bypass it. So there was a bypass for that restriction. And the next thing I want to show you guys is just an old demo that I used. So you can see that I'm starting from a very low privilege user. Just adjusting the symbols there. So I triggered the overflow. You can see that the memory getting allocated is of 10 bytes of size, which is not what the object expects. Next part in the function, you can see how the pool is in a deterministic state. I allocated actually bitmaps and palettes in a certain series of allocations that got the pool in a very deterministic state, and our object is allocated at the end of the page just before one of the bitmap or palette objects. The GDI object dump is actually a win and debug extension developed by Diego Juarez. I had to modify it to work on the current. It shows you the original size of the bitmap, and then after the overflow, what I used was to actually overflow the size to multiply it by 6, which extended the size very widely. And now I'm able to read and write from kernel memory. Now I'm looking at the adjacent palette that is allocated, that its original size is 1E3, and after I use the bitmap or the corrupted size of the bitmap, I successfully corrupt the size of the palette to max int, which means I can read and write up to 4 gigs of memory from that location in memory, the location of the first palette. Now what I want to do is to overwrite a pointer for a second palette that is near the first palette. You can see this is the original pointer. And what I'm gonna do is overwrite it to the location of the original bitmap to fix its headers, because if I'm doing an overflow, the headers got clobbered. If I leave it in that state, when I exit the program, it will result in a blue screen of death, which we don't like as exploiters, since we want a stable exploit. So now you see I already modified the p1st color to point to the overflowed bitmap header. I will show you now the overflowed bitmap header data. So this is how the data looks like in an overflowed palette. And after I called write to address, you can see I successfully just like modified the palette memory in the kernel. Now I'm going to show you the eProcess structure, which is a structure that is allocated for each running process on the system that contains specific data. Interestingly enough, it contains the security token. This token, if I'm able to read and write in kernel memory, you'll be able to assign this token to your own process and gain elevated privileges, as you're going to see. So the first process is a system process, and this is our current process. You can see it has a different token and a current process token that shows the permissions that these processes have on the system. So after that, I just write to the eProcess token, and we look at our current token that we have in our process. We'll notice that it was modified to the system process 1. And if I just continue execution and run cmd.exe, you notice we dropped in a shell, and from a low privileged user, I gain system level access to the system. Well, that's it for the offensive part of the talk. I'm going to give you and show, Ian is going to walk you through how we actually started thinking and mitigated that type of object abuse in kernel memory at Microsoft.
Hello. All right. So my name is Ian Kronquist, and Salf has shown you how over the past several years, clever people like Salf and his buddies have figured out a reliable, effective, stable family of exploits in order to escalate privileges. So say you're an attacker, you're in prone to own, and then you figure out how to pop edge, and then your next step is I need to be a more privileged user to deliver my final payload. So what people are doing these days is they're attacking the in-kernel driver system, Win32k or NTGDI, as it's sometimes called. And so, we go ahead and fix the bugs they find, and someone else finds another one, reports an MSRC case, a pwn-to-own submission, something pops up in malware. This is a game of whack-a-mole. We can't fix every bug. And so, this is a systemic problem. And in the face of a systemic problem, we need a systemic solution. And this extends beyond the Windows ecosystem and the problems which we have at Microsoft. Linux has similar issues. And there are people working hard to get more mitigations into the Linux kernel as well. So if we have a systemic problem, we need a systemic solution. In this case, it's mitigations. We want to make the bugs more difficult or even impossible to exploit. So we want to raise the bar for hackers. Fortunately, at Microsoft, we have a lot of historical MSRC data of all our vulnerabilities, everything. Salf has shown us, and people looking for bug bounties, they've reported it. And you can see that we looked at it in order to decide how do we want to design our mitigations, what's most important to tackle first. And we chose this big red sector right up there, use after freeze. Of all the types of bugs which we found in Win32k, 23% of them are use after freeze. And use after freeze are a relatively consistent class. So it's a great target for a mitigation. So then I want to talk to you a little bit about our threat model. What is a threat model? what we assume the attacker can do when they're trying to attack the system. So we assume that the attacker has found a use after free in one of the NTGDI or NT-user types, and one of the few types which we protect. We don't protect everything. I'll tell you a little more why. And they can cause this UAF to happen at any time whatsoever. We assume that the attacker does not have an arbitrary read-write value, or read-write primitive. A use after free is something you use in order to create an arbitrary write. If you already have an arbitrary write, who cares about the mitigation? You already own the box. However, we want our mitigation to be safe in the face of an arbitrary read. There's no particular reason that it shouldn't be, so we should be conscious of what we think the attacker can and cannot do. And that's our threat model. Now, not in our threat model is, like I said, if you already have a write-where vulnerability, you've already won. We can't stop you. You can modify our data structures. You can modify more important kernel data structures. And for a variety of reasons, we only protect a limited number of types. We only protect some types because we wanted to roll this out incrementally. Microsoft's a big organization. We couldn't risk being able to turn it on everywhere and then finding there was a regression for one obscure type, which is only used in a couple places in the code base. There's also some memory impacts. There's introducing this new heap I'm going to tell you about. It takes up a little more space in the kernel. And while that's acceptable for a few types, if we were to do it for every single tiny little type, which probably isn't exploitable, it would have a large impact. So what we decided to do is we looked at using that historical bug database, what types were being exploited by Salf and his buddies, and what types they were going to turn to next. Like, are there similar patterns which we can see? Did Salf say this talk? After this type, I'm going to exploit this type if they patch it. So that's how we chose, what to protect. The mitigation I'm going to talk to you about today, we call it type isolation. It doesn't protect against UAFs, or it doesn't prevent UAFs, rather. It makes it so that you can't take a UAF and then turn it into a vulnerability, a write-where primitive. It just makes them very difficult to exploit. And I'm going to explain how that works. It's also important to note that since use after frees have this weird time element, a lot of vulnerabilities you overflow the integer, and the next instruction you can write anything anywhere, and you can detect the integer overflow right after that instruction. Use after free is you've got this dangling pointer. It could dangle for minutes, hours, days, who knows. So in order to catch all the UAFs, you actually need to check every pointer dereference, and that's incredibly slow. That's something which you can't do in the kernel. Windows would just slow to a crawl. So this is something where in the kernel you have a lot of interesting considerations which you have to think about when you're designing your mitigation. So we've designed it so that even in the face of UAFs, as they inevitably occur, that's our assumption, UAFs are going to happen, but the attacker's not going to be able to take them and exploit them and escalate privileges like Salf showed you. So what we decided is we want to deny the attacker control of memory. If the attacker controls where these objects sit and figures out a way to overlap them, then he can make the primitive happen, which Salf showed you some of his later slides. So, it's the layout and contents of memory which really matter. So we changed the layout of memory to be harder to exploit in the face of bugs and deny the attacker control. Deny the attacker control of memory, stop the use after free from being a exploitable vulnerability. So what we've decided is there's two ways, two things we have to protect against. The first is you've got two different types of objects. That blue guy up there, that orange guy, object A, object B, maybe one's a palette, maybe one's a window. And, you've got some pointers in object B, and some color data for like the GDI subsystem, which the user in their application can, change whatever color to make the screen blue or orange or whatever. And then, by changing the color data to look kind of like a pointer, they can now, read and write memory, just like Saif was showing you earlier. So we have to prevent objects from overlapping with each other like this. We need to isolate these two types and keep them away from one another. And then there's another scenario, and this is kind of a variation of the first. What if you have two different objects, object A and also object A? They're both the same type, but they're at like slightly different offsets. There's a pointer in there, there's some color data, and you manage to make the offsets line up just right so that color data and that pointer's on top of each other. Well, this can be another problem. We have to prevent this scenario too. So we looked at all of this and we decided, okay, these are the two things we have to stop in order to stop use after freeze from being exploitable. So, one of the problems we encountered, though, is that bitmap object, the palette object, they're variable sized. You can have a big palette, a little palette, a big bitmap, a little one, and so that makes it difficult to prevent bitmaps from overlapping at each other. And if we can't stop bitmaps from overlapping at each other, like half of Saif's stuff still works. So we decided, what we're going to do is we're going to realize that there's a fixed size part up there in green, and there's a variable size part in blue, this array of user-defined color data. And we're going to put the fixed size part in the type isolated heap. Only that chunk of the palette object is going to live there. And then that variable sized array, that'll just live in the general heap. And so that way we can't overwrite that metadata, that fixed size metadata full of flags and pointers in the palette header with the variable sized user controlled color pointers or bitmap data. So I want to talk to you a little bit about the data structures we use to make this work. We decided, each of these types, they're going to be in their own heap. How do we want to decide, the layout of this heap? How do we make it efficient? Well, since each object is of the same type, one of the most efficient ways to track which objects are free and which ones are used is to just have a big bitmap. And you've got a 1 if the object is the slot in the heap is being used by a palette, or a 0 if the object in the heap is isn't being used right now. And we also make sure, this is important, that every empty slot is zeroed once a free happens. So that way there's no like old dangling pointers sitting around in that old stale object. So I want to walk you through 2 use after free scenarios and show what really happens when we try and use an exploit like Saif's on this new type isolated heap. So the first scenario, we've got some other object up there in blue. It lives on the general purpose heap. Maybe it's one of Saif's window objects, and we're going to smash the palette object, right? That's what he's trying to do, but we've isolated the palette object now. So when we free it, we get this empty slot, we 0 it, and now if Saif tries to use that other object to write through what used to be a pointer in the palette, that pointer is a null now. It's all zeros. And so when Saif tries to dereference it, boom, we're going to get a blue screen of death, and his exploit is no longer viable. This also resets all the flags and other data down to like a ground state where everything's going to be safe or harder to exploit. All the sizes are going to be 0. So let's discuss the other more complicated scenario. So we know we are starting at the same place. We've got this other object, and it points to the palette, and we're going to free it. And then we're going to, this is where we were last time with that 0'd object. But this time we're going to create a different palette in the same place. Now, this other object doesn't know about it. It's still got a pointer to that slot, but there's now a different palette there, and it thinks it's pointing to the first palette, which is completely gone now. It was erased and replaced with another one. So let's say you try and use Salf's technique now. Well, there's still a valid palette at the other end. So you're trying to, write, via a pointer in the palette, you're still pointing to valid data, data which is in use and properly initialized. And so this makes it so even though, you're pointing to the wrong palette, it's still a legit one. And you can't make an exploit out of this, because all the palette code's going to look at it and go, yep, this is a valid palette. These are valid sizes and offsets and pointers which point to real data, and they're not the hex 4141 which Salf stuffed in there. I want to talk to you a little bit about similar work. Our technique does not stand on its own. Adobe Flash and Google introduced heap partitioning in 2015. This really helped. Adobe had some problems with vectors, some of their vectors in their Adobe special JavaScript engine, ActionScript. And this really helped them. They worked closely with Google in order to design this mitigation. And then around the same time, IE added isoheap, which is a very similar technique. They later improved upon isoheap to add a garbage collector. So now they don't use that, they just use a garbage collector on this native code, kind of similar to the BOEM GC, if you're familiar with that. And then shortly after our code landed, WebKit added a similar feature, and it works. It's pretty much the same sort of strategy. So we've seen, we've got Google, we've got Microsoft, we've got Adobe, we've got WebKit and Apple. They're all using this same technique. It's tried and true and proven to work by a variety of organizations and a variety of hardcore system software, Flash, web browsers. And so, I want to talk a little bit about our impact. Francisco Falcone of Quarks Lab wrote a blog post reverse engineering our work. And he said, at the time, we had shipped it for just the surface object, just that bitmap object, which Salf showed you. And now we've expanded it beyond that. And he said, this definitely eliminates the commodity exploitation technique of using bitmaps as targets for limited memory corruption vulnerabilities. And then in the next sentence, he says, and then I'm going to use the palette object, just like Salf showed you. So now, by the time he wrote this blog post, we were ahead of the game. And we had already in Windows Insider builds, like beta nightly builds, which you can sign up for, and explore all the latest cool features, both in the GUI and in the kernel deep down inside. By the time he had written this blog post and posted it, we had already protected the palette object, and that code was out the door. And so if you're on the latest version of Windows, you definitely have protection for the surface object, like to prevent some of the exploits I showed you. And then if you are going to be on the soon-to-be released RS4, then you'll get all the other goodies and protections after that. And we're not done yet. We have a list of other objects which we're interested in expanding this protection to. Attackers, are going to start looking for the types we didn't protect, like I said. But, we've got a plan to expand the protection to protect all the objects which we believe are exploitable using this style of a use after free in NTGDI kernel land. With that, I'm wondering if you guys have any more questions. It's still early in the morning. Not everyone's had their coffee yet. All right. I want to thank you guys so much for coming here. I want to thank Nixu and Hack in the Box. And I hope you guys have a great time. Feel free to walk up and say hi to Salf and I. and ask us questions about the mitigations we design, the fun stuff we're finding in MSRC, the vulnerabilities they're cooking up. And thank you so much.